Hello, and welcome to the session about how Disney streaming services and TrueCar deliver web application for scale, performance, and availability. My name is Tal Shalom. I'm a senior solutions architect with AWS, specialized in edge services and perimeter protection. We have an exciting session for you today with two of our customers coming from different industries and presenting different use cases. Both are dealing with scale challenges and migration concerns. So before we dive into the solutions, let's meet our presenters.
Hi, my name is Regis Wilson. I work with TrueCar. I'm a site reliability engineer for about 4 years. TrueCar is a digital marketplace for automobiles, and we allow consumers to search and find their perfect used or new car. We have been responsible for about 5% of used car sales in the United States last year. So very happy to be here. Thanks.
Thank you, Regis. And from Disney Streaming Services, Achintya Ashok.
It's a pleasure to be here. I'm Achintya. I work on the content discovery team at Disney Streaming Services. Disney Streaming Services is Disney's arm of creating its flagship direct-to-consumer video streaming platform. Prior to being Disney Streaming Services, we were formerly known as BAMTech, where we were pioneers in the streaming and the live streaming space, and we created solutions for the likes of MLB, MLB TV, Eurosport, NHL, and ESPN. So it's been a long transition, but we're excited to bring a lot of the new stuff to your devices.
This is great. Thanks for being here with us. So while we have you here, let's start with your solution. So you're adding now more premium content like live sports, new shows and TV. That brings a lot more traffic to your site. Can you tell us what is your team responsible for within the entire content delivery chain?
Yeah, absolutely. I mean, Disney is a pretty large company, so I think that's a good place to start, delve deeper into exactly what I do and what the team does. So again, I'm on a team called Content Discovery, which primarily deals with all the metadata required for presenting knowledge about the catalog that's available, anything pertaining to recommendations, delivering recommendations at scale. Specifically, one of the APIs that we build is called the Search API. And this API is kind of the primary metadata service that all end user applications will hit to load anything on their devices. So it doesn't matter what platform you are, if you have an Apple app or you have an Android app, Samsung, Apple TV, whatever it may be, at some point in the life cycle of the device, the application is going to hit the Search API, and that's going to be its trigger for loading any content on its page. So suffice to say, it's a pretty critical thing. If it doesn't work, then you're going to see a lot of degradation in your application, and in fact, you're not going to see anything. So we serve anywhere between a few 100,000 requests per minute to serving over several million requests per minute, depending on the scale and depending on how many users are currently using the service. So user experience just depends critically on this being fast and reliable.
So with this newly added content and the increase in traffic, can you share with us what was the starting point? What were the challenges of the existing architecture?
Yeah, let's step back a little bit because Search API and content discovery wasn't as big or important as it is currently. So where we started our humble beginnings was basically acting as the search service for a subset of our partners. And by partner, I mean MLB TV, Eurosport, ESPN, whatever it may be. But as we started to see this consolidation, as our responsibility grew within the company, we became the primary metadata service, the primary line of fire for this page load metadata. So we've basically transitioned from being a pretty simple REST API to having to deal with all of these different platforms with all this relevant data that they need. So we've had to architect our API using GraphQL, which gives us the capability of creating a schema of all the data that's available and allowing any platform to really pick and choose what content they actually want to get. So that's what GraphQL gives us in terms of flexibility. However, with that, it also has a darker side. So GraphQL is pretty CPU intensive, which we'll get into how that's influenced our architecture, influenced our design, and influenced the way in which we scale. But coming back to it, we were serving anywhere between 30 to 50,000 requests per minute, which isn't a small number, but it isn't a gigantic number either. There are other services out there that do far larger volumes. But we started to move towards this setting where we started to predict that we'd be servicing upwards of 5 million requests per minute, which is more than a few magnitudes larger than 50,000 requests per minute. We were also in a single pool in a single region because we weren't that critical of a service. But now that we had the service that had to stay up, that had to remain extremely low latency, we had to basically develop a pattern in which we could stay up by having our APIs housed in multiple pools across multiple regions. In case if one region fails, we still have other regions. If one pool fails, we still have other pools. And finally, we had pretty variable latency, but now, given this critical standpoint, we had to stay within the limits of servicing the lifecycle of a request within 100 milliseconds. And the last point is that initially we didn't have any form of personalization happening, but now that we saw users coming in from multiple different countries, from multiple other variables influencing what metadata that they should get, our API basically had to be re-architected in such a fashion as to deliver both semi-personalized and personalized content, such as recommendations. So suffice to say, there was a long road ahead.
These are ambitious goals. I wonder what was the starting point from a design perspective and how those challenges reflect into the actual architecture that you started off?
Yeah, let's actually dive a little deeper because we need to kind of understand the architecture of this entire thing. So the diagram on the right basically depicts the overall structure of our initial application. At the top, we had Route 53 handling all the DNS. All the requests would go through there. They would end up at the load balancer level, which would then split up those requests across multiple origin servers, denoted by the Search API boxes. And the Search API instance itself lived on EC2 nodes. Below that, we actually had a data layer comprised of both Redis in the form of Elasticache and also Elasticsearch as our true source of data. Now, if we talk about kind of the behavioral patterns that we saw with these incoming requests, you have to remember that we were live streaming a lot of live events. So think of it as in the English Premier League is happening and there's a match between Manchester United and Chelsea. A lot of people are going to sign on 5 minutes before the actual event starts. Fortunately or unfortunately, for us, we have to deal with that. And what this produces is basically a huge influx of requests coming in at exactly the same time. So we call this a thundering herd problem. You probably know it as something different. But basically, we're to contend with this, and given the fact that we're a pretty experimental team, we kind of followed a pattern of experimentation at this application layer and this data layer as to how we could scale.
That's interesting. So it sounds like you needed some more compute power at the API layer. Wouldn't be just adding auto-scaling at the API layer and maybe scale horizontally to accommodate those spikes of thundering herd, or some others might know it as a flash crowd, as a different term for that?
That sounds very optimistic, but in reality, that's not how it works. You can't just throw an inbuilt solution at something that's a little more complicated, a little more involved, like this is. So there are basically two forms of scaling you can do at your application layer. One is vertical scaling, and the second is horizontal scaling. So in terms of vertical scaling, what this actually means is that if your bottleneck is CPU, then you're going to add more CPU units to your resources to allow maybe each of those instances of the API to handle a larger volume of requests. So initially what we did, our naive approach was, okay, we're running on C4s, let's make it a C4 2XL, let's make it a 4XL, an 8XL, a 16XL. But as you can imagine, there's a limit to how many different types of XLs you have available to you, unfortunately. And moreover, this is a solution that doesn't really scale well with a variable number of requests coming in, because you might provision a really big node, but then at some points you might just have a trickle of requests coming in. which means you have over-provisioned, you're overpaying, and it's a solution that's not feasible. The second form of scaling that we started to experiment with was horizontal scaling. And essentially what that means in a nutshell is below this load balancer level that's splitting requests across the API, you basically add more nodes. So in this depiction, we have 3 different instances of API running on EC2 nodes. So rather than 3, we scaled up to 6, maybe 12, maybe 72. But again, you run into the same sorts of issues where you're over-provisioning for a lot of the time that you don't need that over-provisioning. And secondly, bringing up each new instance of our search API was a life cycle of about 10 minutes. So when you're under duress, when you have this thundering herd problem, and it takes 10 minutes to add each new node, it's just not feasible because by the time that node comes up, either the traffic is gone or you have a lot of unhappy customers. So it doesn't work out. So basically, neither vertical or horizontal scaling on this application layer was a feasible solution.
That's interesting. So we still have the problem there, but I also wonder about the data layer itself. Let's say you get more requests or this spike, was the data layer ready to, for that load, for that scale, to support that scale?
In an ideal world, even if your application layer scales, you've uncovered a good point. At the end of the day, it's going to have to go to this data layer. It's going to have to get the data from somewhere. The API doesn't have any concept of some ephemeral storage. So the way that we architected our application was Redis was a key value data store for us, in which we basically had an L1 cache of our data. So a request would come in, it goes to Redis. If it can find an appropriate response, it bubbles it back up to the user. If there's a cache miss, then we go to Elasticsearch, which is our true source of data, fetch the metadata, cache it in Redis, and then bubble it up again to the user. But we run into this similar horizontal and scaling issues for Redis. The way that you provision Redis is you can specify a number of nodes that you would like to have in a Redis cluster. Adding nodes is not that simple because, again, it takes some time to actually spin up those nodes and get it into the cluster. And second, just changing the instance types of your Redis nodes themselves takes a lot of time to provision, and sometimes you might need to provision an entirely new Elasticache cluster or wait until it's ready with the new node. So even that isn't feasible. With Elasticsearch, unfortunately, the problem gets even worse. Elasticsearch is great for just doing a fuzzy search on things. And the way that it's basically architected is that it distributes the data by sharding the data across the number of nodes that are available. In real time, if you add new nodes, Elasticsearch has to go through a process of rebalancing the data across the new nodes. And that rebalancing process itself is blocking. So Elasticsearch will start blocking some of those incoming requests while it executes this action of rebalancing the nodes. So if you start to rebalance your Elasticsearch cluster under duress, you're suddenly going to exacerbate your problem even further. So with this, we saw Redis throttling, we saw Elasticsearch throttling, and then we saw our response times just shoot up beyond 100 milliseconds. So there are a lot of problems even with the data layer.
I see. So if I summarize up to this point, your team took an experimental approach to look whether throwing more compute resources at the API layer might not be the optimal solution, and then still supporting this spike at the data layer might create a bottleneck which will impact the latency on the request response time, affect the user experience, and at the end might hurt the business,
yeah, absolutely.
basically. So those tactical solutions seems not feasible, and you needed more of a strategic direction to take here. So I wonder, what was the next step? What was the strategic direction?
So, as was shown here, scaling is not, you can't just throw out of scaling at this, it doesn't work. So we knew that we had to basically push compute to a layer above all of this. If we could push compute to a layer above our APIs, above our data layer, we could enable ourselves to basically handle a request at this compute layer without ever going back, without ever exacerbating CPU due to GraphQL, without ever exacerbating this issue with rebalancing in Elasticsearch. So basically, for us to adopt this solution, it had to satisfy 3 basic needs. One was some form of edge caching. So edge caching in which A request comes in, and you immediately have a cache hit on whatever this compute layer has, and it returns back the response without ever going back to an origin server. Second was auth token validation. So essentially, we're passing user information in part through an auth token, in which we extract information such as the location for the user. So we need some fashion by which in this compute layer we can crack the token, we can validate the token, and we can also extract out meaningful details to return back a response pertinent to the user's location. And finally, we'd moved to this setting in which we no longer had a single pool in an API or in a single region. We had multiple pools in multiple regions. So we had to have some intelligent fashion by which we could dynamically select the origin. All of this while basically keeping it, in terms of a global availability, highly available, and also keeping that response time, that critical metric that we had below 100 milliseconds. So given all of this, given a little further research that we did, the solution that we landed upon was, in fact, CloudFront with the addition of Lambda Edge. The reason being is that CloudFront basically acts for us as an edge cache. So, a request comes in, if it can get handled through this CDN, it gets handled. In addition, we can do a lot of computation through Lambda Edge when it's applied in CloudFront. So we can do all of that token validation, token data extraction, and also dynamic origin selection directly at the CloudFront layer. The other thing was CloudFront was simple for us to set up because we only had to set up a single distribution, and it was globally available immediately. So it's not a solution in which, oh no, we're now servicing users in France, set up a CDN in France. Luckily, CloudFront took care of all of that for us in a very simple approach. And there was no manual scaling required. So as I mentioned, you might have scenarios in which you have a trickle of requests, and then you might have scenarios in which you have an extremely high volume of requests coming in within the span of 5 minutes. So CloudFront was able to basically handle this very gracefully.
So you basically took the approach of serverless and you pushed it to the edge, pushed some functionality to the edge, as well as taking the benefits of CloudFront scale and offloading a lot of those requests to a caching layer at the edge closer to the user. So I'm very interested with the implementation itself of the functionality in Lambda Edge that you did. But before we dive into that, let me take a moment just to explain what is Lambda Edge, how is it different than AWS Lambda, and how it works with CloudFront. So Lambda Edge is actually an extension of AWS Lambda. It allows you to take your serverless solution to the edge and execute functions that can customize your content closer to your viewers rather than all the way back at your origin servers. The functions can be associated with CloudFront. You basically write the function in US East 1 region, and once you publish the function, it's automatically replicated to other locations globally. And then once it's associated with CloudFront, you can trigger the function in 4 different spots within the request response flow. The first one is at viewer request. That's when CloudFront receives the request from the user, and then before it hits the cache layer. And then the second is at the origin request, if most likely it was a cache miss, so you can trigger the function at that point. And then similarly on the way back on the respond, on origin respond, before it actually gets to the cache layer, and at the viewer response before CloudFront handing back the response to the viewer. So I wonder which one of the triggers did you choose, and what functionality you implemented with Lambda Edge?
Out of the 4 triggers that you've mentioned here, we basically used 2 of them. One was a viewer request, and the other one was the origin request. So let's get into specifically why we utilized the viewer request. So again, as a recap, the viewer request is the one that gets invoked when a request immediately gets handled by CloudFront. It invokes this viewer request, Lambda. So as I mentioned before, we were passing some user information through the auth token, right? So think of the auth token as basically just a header on this request. It's an authorization header, and the value for that header is going to basically be a JSON payload that's encrypted in some format. So what we do is, in the viewer request, the first thing we do is validate this token. Is it coming from a knowledgeable resource, or is it coming from some bad actor? Secondly, what we do is we're passing a 2-letter country code in this token as to where the user is coming from. So if the user is making their requests from France, there'll be a geocode of FR within the token. And if the user is coming from Germany, there's going to be a geocode of DE within the token itself. Now, the question naturally arises, what are we doing with this information? So I'd like to point out an example in which, let's say that you're trying to load the Bundesliga schedule. So as a user in Germany, you would expect to see all of your titles and descriptions and any other metadata in German, because German is the language that you're naturally attuned to understanding and speaking. As opposed to, if you're a user in France, if you saw something in German, you probably wouldn't know what's going on. So you should see that same data in French. So what we do is we take this geocode and we map it to an actual cached piece of metadata, and we return back the cached metadata pertinent to the region. This way, we're basically semi-personalizing the response to the user directly at CloudFront. So that's enabled us a lot of flexibility to basically semi-personalize responses on the fly at the compute layer itself. Request never goes back to the origin. The second way we use this is through a concept of something that we refer to as media rights. Think of this as essentially you as a user, you've purchased a subscription to the English Premier League. So you should have access to anything that's in the English Premier League. You should be able to stream their events, you should be able to see the catalog of stuff, but if you haven't purchased it, if you don't have access, then maybe you should instead see a message saying, hey, you don't have access to this, go ahead and purchase it, and then you'll get access. So we use this media right information, again stored on the auth token, to determine whether the user has access or doesn't have access, and we either return back to them the metadata for the content they're requesting, or some response indicating that they don't have access. And the applications can take care of displaying that logic whichever way they please.
Got it. So you mentioned before that you used viewer request and origin request functions. And viewer request, basically, you're hitting with every request, so you can do different manipulations. But why did you need an additional function on the origin response?
Right. As you mentioned, the viewer request gets invoked on every single request. But the origin request only gets invoked when there's a cache miss on CloudFront. So let's say that you don't have a cache hit on CloudFront. It's going to invoke this Lambda, which is going to basically say, where should I route this request to? To what origin server should I route this request to get back a response? And so now that we're in this scenario in which we have multiple pools of APIs in multiple regions, depending on how our development process is, we basically follow a continuous integration approach, in which we basically roll out changes pretty frequently. So a scenario might arise in which a pool A of our API has some feature enabled, and a pool B of our API doesn't have that feature enabled. Now, it's perfectly predictable for the request to be routed to either one of those things if all else is equal. So what will happen is, Tal, if you come in and you make a request, say you want to watch the latest English Premier League match, which is usually pretty exciting. I would watch it too. You make a request, that request comes into pool A, and you get back a piece of metadata. If your subsequent request goes to pool B, which doesn't have that feature enabled, suddenly you'll see a difference in the metadata. Your behavior in your app will change. You'll have an inconsistent flow in your app, resulting in a degraded user experience. So we have to certifiably say that you as a user, if you come in, we're always going to send you back to the same pool so that your behavior, so that the interpretation of your application doesn't change. So what we do is we basically follow the canonical hash map approach. We have all the load balancers, all of our origins, in basically a bunch of buckets. We take your IP, that's available to us within the origin request, and we hash it across all of these buckets. And so we can always, using this one-way hash function, always guarantee that you're going to end up at the same origin server. And by that way, we basically mitigate this scenario that could arise. So this is also easier for us to do rather than handling DNS records. So DNS records, while they're vital to the whole flow of the internet, it takes time to propagate a change in DNS. It takes time to update a DNS record based on the TTLs of the DNS record. So through the origin request lambda, we could basically publish a new origin request lambda with an added region or a removed region, or removed pool rather, to basically dictate what's available for a request to go to, rather than having to make any changes at the DNS layer. So it gave us a lot of flexibility in that regard too, and so it worked really well for us.
Interesting. So we see here two main uses for Lambda Edge. One is inspecting an auth token and personalizing content, and also dynamically divert the request to a specific origin server. There are many other use cases that you can use with Lambda Edge, like A/B testing. You can do network calls to other services. And you can even generate a page. You can generate a response right at the edge. So looking at what you're currently doing at the edge itself, I wonder what are the performance that you saw after implementing that, and was there any event that you actually used that architecture so far?
Yeah, so this is a fancy new architecture, and as an engineer, you're always attracted to shiny new things. You always want to test out new things, talk about the new things you've worked on. But at the end of the day, no matter how fancy any architecture might be, at the end of the day, it needs to perform. Otherwise, it's a non-solution. So I'm happy to say that even with this new architecture, we basically verified that it gave us significantly improved performance. The way that we elicited this information was when we had two really major events happening at the same time. One was the 2018 Winter Olympics, and the other one was one of the most highly trafficked Bundesliga events this year. And despite having these two things happening, not on their own, but simultaneously, we saw 0% downtime. We saw our latencies well below 100 milliseconds. And I think what best depicts this are the two graphs. So the graph on top is basically the number of Lambda invocations happening. And the graph on the bottom basically depicts the number of requests being handled at the API layer. So that large amplitude that you see in the middle is one of those thundering herd issues where everyone is signing on at the same time. It's a massive spike. It looks like a massive anomaly within the graph, but it's a perfectly normal scenario for us to handle. And what you see is that Lambda Edge is handling a significantly higher magnitude of requests than the API is. So it's basically eating up a lot of the load and preventing that load from even going down to the application layer. And with this, we essentially saw that our CPU in our API layer remained well below 5%, which was our target. We saw our average latency below 30 milliseconds, despite these new Lambda Edge triggers. They added about between 5 to 10 milliseconds in terms of response time. But given the way that CloudFront is architected, it takes advantage of the geographical nature of where the request is occurring by routing it to the closest node and handling it at that closest node, which also gives you a geographical advantage. So that's something we didn't really think about, but it gave us, so it was a nice thing to discover. So we had a scenario in which we had 48 API instances handling between 100,000 requests to several millions of requests, and it didn't have to do anything in terms of scaling. So to us, this was the perfect solution to get us out the door, and this is what we currently use and will be launching with at the start of Disney+.
Amazing. So you took the approach of serverless at the edge, leveraging CloudFront scale, leveraging the fact that Lambda Edge can scale automatically without you needing to provision those resources, and offloading a lot of the stress from your API layer. Thank you, Achintya. I know you can keep talk and dive further and further into the solution, and we'd love to hear more about future expansion. Let's keep that to the end of the session.
Sounds good.
And let's change gears and talk a little bit about cars, or I should say TrueCar.
Hi, everybody. Yeah, my name is Regis Wilson. I work at TrueCar. Through our membership and partner benefits that we offer, we reach about half of new and used car buyers in the United States.
So Regis, I know your platform was fully implemented on premises. Can you share with us what was the trigger to make the decision to deploy on AWS?
Sure. Our company goes back about 10 years or more. We have a legacy platform that was developed organically, and it's grown. We had multiple versions of apps, multiple applications. We have multiple teams working on those applications over many years, and it was just very difficult to create and build new applications to deliver new features. We also had a lot of problems trying to coordinate all of our different more than 500 partners that we work with. Some of them have a shared brand where we serve this benefit through TrueCar branding. Say if you're a member of PenFed Federal Credit Union or Sam's Club, we offer it under the TrueCar brand. But if you're a member of USAA, for example, we serve that under their brand. So we're not able to make changes or change these things very quickly. So given all of these challenges and problems that we were having at the time, we decided we needed to take some time to move to the cloud, not just move everything, but actually rewrite it and start over from scratch, basically.
I see. So looking at this architecture on-prem, it seems like you could basically deploy the same services on AWS and in a way of lift and shift, move it over, and then maybe create a template for the migration of your partners and migrate them over. Again, from this diagram, it seems like the feasible solution. What were the challenges with that?
Yeah, I'm glad to see the myth of lift and shift is alive and well.
Yes.
You can't actually lift and shift this. There's way too many complex moving parts and too many pieces going back too far. That diagram's too simple to be accurate. We have another problem is if we need to move the whole ecosystem, if we rewrite parts of it, if we have different teams working at different timelines, it wouldn't be feasible to lift and shift and change it in a night or even a month. We need to move all of our pipelines. We do a lot of data ingestion, processing. The partners need to approve changes in some cases. We aren't able to just release new changes without consulting and testing. We also need to be able to A/B test the new code. If it works properly, we have to pay attention to page speed, load times, conversion rates. We have to make sure our SEO and engagement is up to snuff. In some cases, we can roll out, and then maybe we find that it's not working properly, or we need to test another direction, so we might need to roll it back.
I see. So was the approach to migrate partner by partner, or a batch of partners, or maybe test it first and then just full migration?
Sure.
Did you experiment any of that?
Yeah, absolutely. So we initially brainstormed some ideas here. We might want to move one application to a new application location. We might go one partner and one application, maybe one partner with a group of applications, maybe batches of partners using an application. But one of the use cases that the business wanted was to be able to do a traffic split. So take one partner and one application, split off 50% of the traffic, maybe for taking a whole application across all partners and moving that by a certain percentage traffic.
So if I'm looking at those options, this complexity calls out for some sort of a routing engine. And if you use each partner domain, I would think that using a DNS as your routing engine and just pointing to the right application might be the solution. Did you guys consider that?
Well, sure. There are several typical migration paths. DNS is certainly one of them. It's the first one we looked at. The problem is that it moves an entire partner's traffic all at once. And so for some of our very big partners, we couldn't just switch them over and then hope that it worked. And then if we needed to roll back, it would be very tricky to roll back and take a long time. We looked at some other application migrations, which is to do it at the application layer. Say we use an Nginx or some sort of proxy. Typically the problem here is you have good control over the application layer, but by the time you've hit this application or this routing engine or this proxy layer somewhere, it's usually too late. Maybe you've already hit a cloud endpoint or you've hit a data center, and then you have to go route it back out to the cloud or back to the data center. This is usually too late. We also looked at using CloudFront rules. We could use ALB target groups perhaps to map traffic correctly, but it takes a long time to roll the CloudFront behaviors out. If you imagine we have more than 500 partners, even if we bucketed the partners into distributions, we might have 10 or 20 distributions. For each application, we would need to migrate and change those application rules for each distribution across multiple distributions. And it takes a long time to roll out, it takes a long time to roll back, and you can't split the traffic that way.
See, but I still see that you have the legacy platform active, and you have the new platform, and I understand that you're migrating, either partner by partner or a few partners, but you still need to control the routing between the on-premise platform to the AWS deployment. And by this, architecture, it seems like CloudFront is the natural solution. Looking at that as two origin endpoints, one is a custom and one is within AWS itself. So what was the exact challenge when you used CloudFront?
Sure, so we came up with this idea that we could use Lambda at the edge to make decisions on the fly to route to new origins. We would implement some sort of routing rules engine that we could update in real time. And then just as you mentioned, the origin request function could make a decision when the request came past the cache miss, and it would go to make a decision, should we route to origin endpoint A or B? And this was the architecture that we designed.
So looking at this architecture, this is a great idea to use DynamoDB as your object for taking parameters, making decisions, basically using Lambda Edge to make a network call to DynamoDB where you can update faster and you don't need to rely on updating the Lambda Edge function itself. And this solution seems like it can be used in many different use cases and different industries. Can you dive a little deeper about how the decision-making object looked on DynamoDB, how Lambda Edge interact with the DynamoDB, and how it executed?
Sure, so if we zoom in on the DynamoDB design, we have to support traffic in the United States on the East and the West Coast typically. So we used global tables, DynamoDB global tables. This allows us to write to one region, let's say on the East Coast or the West Coast, and it automatically replicates. They're master-master, so we can write to either one. Any request that comes in on the edge, it can execute in Lambda at the edge wherever the end user is located. So in this example, US East 1 and US East 2, pretty close to US East 1, so they share that DynamoDB region. If a request comes on the West Coast, US West 2, then we route to the closest DynamoDB table in US West 2.
Interesting. So you're using Lambda Edge as your routing engine, but you take the parameters from DynamoDB where you can update that, and that's on a global table. So you have the option to access in different regions. Can we dive into the actual object? I know you wanted to share with us some of the code examples, how the object looked like.
Yeah, we're going to take a deep dive into the technical details here. So this is a JSON blob which stores very well in DynamoDB. We take the host, which is the partner name or the brand possibly. That's the hash table. And we take the URI, which is the path of the request, or the application name. That would be the range key. So taking the hash and the range key, we get a unique action. And you can see there in the green, we have a possibility of setting the origin. We can set it to the cloud or the legacy sites. And in red, you can see we can change the URI on the fly. We can rewrite it to index.html for the legacy, or maybe something more modern like /home. We also have a weight there. I'm sorry, missed that part.
Okay.
Yeah, we have a weight, so we can evenly distribute traffic, 50-50 in this scenario.
Got it. So this is the parameters and then the execution.
Yes, this is a code example. It's written in Node.js. We have 3 matches that we can do in a hierarchy. So the first match, maybe the most specific match is the one we want to do first, the exact match. We can do a partial match on the URI, which might be part of the application name. Then we can have a default or a fallback. If you look at in the fuchsia, there's like a execute action. This is where we actually make a decision on which result to return. And then based on that, we can do a response in the green. We can actually generate a response back to the client on the fly without going to the back end. We could send a 301 or a 302. We could send out even a page saying, go check this out. Or we can send the request back to the back end.
Got it.
And then going further, zooming into the execute action, we have 3 actions here just as an example. We can set the URI to a new value if it's present in the JSON. If it says to set the headers, we can set arbitrary headers and response codes. And then in the most critical case, if there's a set origin parameter there, we can change the origin as well.
I see. So before you mentioned that there's the option to do a weighted routing, and you're using Lambda Edge at view request. So every request that comes in, you're making that check. How do you keep each user to go, to the same origin? Are you using any type of a session cookie that you track? Is there any mechanism?
Yeah, absolutely. As Chintia mentioned a little bit earlier, let's say you go to our website and we pass you along to one of our experiences. We need to be able to make sure that your next request will go to the same experience, not a different one. And so we were using a feature called Launch Darkly in our application already. Software engineers use Launch Darkly to create feature flags. The feature flag allows you to say this experience is turned on or this experience is turned off, make this button red or this button green. And we were able to leverage that in Lambda at the Edge. We use the same flags that the software engineers use in building their new applications and their experiences. So when the request comes in, let's say a user token has already been targeted to experience A, the request will come into Lambda at the Edge. We'll see that same flag is enabled for that user is set to experience A, and then we'll choose experience A. You can see in the green, if the flag matched, we would go to the first one, and if it didn't match, we would go to the default.
I see.
And here's an example of how we would rewrite this JSON blob. In this case, we can take in the green, the Launch Darkly key, that's the name of the key. So this feature says this partner home has been launched. If we see the value is Challenger 1, then we go ahead and route that request to the origin, to the cloud. And if it was Control or Challenger 2, we would just send it to the default.
Regis, there is a lot going on at the edge, with this implementation. You have a call to DynamoDB. You have another call that goes to an external service to get those feature flags, and all this process at the edge. You also mentioned that you wanted to maintain a low latency. I wonder how much this impact and affect the overall latency.
Yeah, we also had a 100 millisecond budget, similarly, as Chintia mentioned. When I first wrote the original proof of concept, it came back in response times of 300 milliseconds or more, which is a third of a second. That's way too much. That's way too long for a user to wait for a page to even be returned. So we were able to find out, searching on the internet and asking for enterprise support, if you scale the size of the Lambda memory, you get more CPU slices. You also get less yielding in your code. And so as we scaled the size of the Lambda up to 1 gigabyte, we're able to bring response times below 50 milliseconds. And here are the actual results from production. You can see our average latencies, or I should say the average runtime of the Lambda execution. which turns into latency for the end user. But in this case, it's less than 50 milliseconds. Our 95th and 99th percentiles are right where we need them to be. You can see that US East 2 is a little bit higher than US East 1. That's because it's a little further away in that diagram I showed you.
That's an important point to mention when you do requests to a failover location. That might increase a little bit the latency, but still, as we can see, you're under your 100 millisecond budget. So, Regis, this is great. I mean, seeing that migration over, taking approach of serverless architecture, pushing functionality to the edge. Chintia, why won't you join us again, and let's talk a little bit about the future. What are you planning for future expansion, and which features are you looking to implement?
Yeah, so we're basically trying to figure out right now, all of our routing rules are set up in JSON, so there's no requirement for a business person to ask for my intervention when we make changes to our routing. But in order for new routes to be created, someone needs to be doing that, usually me. We want to create an administrative UI that allows non-techs and maybe business owners to actually, maybe even just to view the rules that are in place. But also at some point, you'll be able to click new and add a rule, and add a new route to the new application that you're building. We would like to be able to roll out these changes in a controlled manner, or maybe on a schedule, and then be able to roll them back with one button, let's say. We'd also like to be able to see all of our environments in one place. So if you have a QA and a staging and a production set of rules, you'd want to be able to view those together, and maybe have like approvals and workflows, that kind of thing. We need to increase the unit tests for our code, functional tests, so that we don't break anything. Right now, we have scripts that check things are working correctly, and we have monitoring, but it's still relatively manual to make sure that everything's running perfectly. And then lastly, if we had better visibility on which routes were being matched and how those routing behaviors were occurring and what the current status was, we'd like to be able to see that.
Thank you for sharing that with us, Regis. And now, Chintia, I stopped you before because I wanted to keep that last point about future expansion.
Right.
What do you guys have in plan?
Well, first of all, Regis, just going to give you fair warning that we're definitely stealing some of your ideas.
Absolutely.
I think you have some good stuff there.
Yeah.
But more than that, I think one of the largest things that we've seen, even over the past 10 years, is we've gone from a scenario in which we've had to provision some form of a host, whether that's local to you or on some cloud provider, with the perfect environment variables, the perfect setup for your application. Then we moved on to a phase in which we were using VMs. We had multiple VMs running on a host, where maybe one VM really was tuned to your application specifically. Now, I'm happy to say, we've moved to a level even above that, where we have this atomic unit, this container that can run on any host, regardless of where that host is, regardless of any factors on that host. So we've really adopted this. We feel that Docker is the future. We've adopted containerization across the board in content discovery, and there's a push towards that in the larger organization of Disney streaming. With that, I think the next step forward for us is really figuring out what the right format of container orchestration is. How do you roll out updates to your app now that it's in this container, in this atomic format? How do you roll it out based on a regional basis, based on feature basis? How do you roll back? So all of these things are a container solution that we need to adopt. So we use ECS currently to do that, and we can really see a lot of growth in continuing to use that, continuing to adopt that, or maybe any other orchestration format that there may be out there. The second is we've moved towards a scenario in which there's a lot of event-driven processing happening across the board. You have these discrete events happening in real time, and you have to respond to it gracefully within a graceful time period. And that's not to say that you should provision an application that keeps polling, waiting for these messages, but maybe you needed a complete event-driven architecture. We use Kinesis a lot within Disney+, within Disney streaming, and we use Lambda a lot as well. So I think Lambda is really tuned towards this event-driven format of information being passed to and fro, And I think we're going to see a lot more adoption in Disney streaming of Lambda specifically. So there's a lot of growth out there, and there's a lot of stuff that we want to look into.
Super. Chintia, Regis, thank you for sharing with us your journey for scale, your journey for migration. This is very beneficial for the community. Any last remarks for our audience?
I'll go first. So just wanted to say thank you to you, AWS, and you guys in the audience for coming and listening to me speak. It's been a great honor for me at TrueCar to work on new technologies, to be able to present information out to the community to share all of our solutions. This talk originally came out as a result of a blog post that I wrote for AWS, which is going to be published on their the CloudFront site, so you'll be able to dive into it more. Also, you can feel free to contact me at any of these locations that I've mentioned here. I think you can see that we have some people with a lot of team spirit in the front row, and this isn't just marketing. I actually do drive a car. So thanks again for coming out and listening. Really appreciate it.
Let's have, thank you, Regis. That's Chintia, if there's anything else.
I mean, I can't top the last statement. Let me just say that. Nor the presence that you guys have. That's great. I have Jim, who's and Brandon as well. So a lot of great people from Disney over here. But first of all, I want to thank the both of you, Tal and Regis, for being here, for having this discussion, and of course everyone in the audience who's shown up here, who has some interest in this. And I really hope that you've come away at least learning something in terms of the technological side, the technical side, or maybe even about Disney. Another thing is I've been using the word we because this has been a very team-oriented approach and very team-oriented effort in content discovery. And along with a lot of experimentation and testing and trying to play with new stuff, that's the sort of format that we work in at Disney, and it's very important to us. Lastly, I want to say that feel free to get in touch with me any way that you want. I think there's a few options listed here. I'd love to hear from you. And finally, there is a Disney Plus tech blog that I would encourage anyone here to visit if they're interested in learning more about the solutions that we're doing here, not only on the content discovery team, but on all sorts of teams, such as the ad tech team. So, in short, as a person who uses a lot of stuff that's out there, a lot of apps out there, I'm always curious about kind of pulling back the curtains, seeing what's behind it. And now when Disney Plus launches next year, and you all get on the service, as I know you will after this talk, and you'll enjoy all of your Star Wars stuff, all of your Marvel stuff, and all of the other great stuff that Disney Plus will offer. And now you'll also have some idea as to what exactly is powering it. So I'm glad to be able to share that. And thank you so much.
Very cool. Thank you. Thank you so much. I hope you find this valuable for your next deployment. Keep sharing with the community. Thank you again, Regis, Chintia. And don't forget to complete the session survey in your Rainband mobile app. Thank you.